Mr. Shams, I'll bet you didn't know that I played basketball in college.
Oh, really?
Yeah, I played for Oregon State University.
What? No, you did not.
Yeah, Division I school, played in the Pac-10, played basketball.
Okay, you're 5'7".
I know. Yeah.
Can you explain this a little further?
Well, I must confess, I did play basketball.
Okay.
But there was, there's intercollegiate, and there's intramural.
Okay.
Now, what does inter mean?
Inter means like an interstate highway goes from one state to another state.
So intercollegiate means
from one college to another college.
So yeah, Oregon State would play UCLA.
Okay.
Or University of Washington.
All right.
Now, what does the prefix intra mean?
It means within the same thing.
So if I played intramural,
you played within your school only.
So McNary Hall played Smith Hall.
Ah, yeah.
Yeah. So I was actually, at 5'7", I was on the McNary Hall basketball team. In fact, we won a total of 0 games.
Wow.
So yeah,
you guys are awesome.
We were really good. So no, I did not play intercollegiately. I played intramurally, and we sucked really bad.
See, I played intramural ultimate frisbee.
Nice. Yeah. I would have done that.
That's fun.
Yeah, it would be cool. So important to understand, we're talking about intermolecular forces. So that is forces between molecules.
Right, from one molecule to another molecule.
Okay. So as we do this, guys, we've got a chart we want you to copy down. So I want you to copy down this chart. Very important chart.
Hit pause,
and print.
file, print.
So this is a very important chart about the different kinds of bonding. All right, so pause and print. I'm going to mark it up, so watch out. Bonding, there's 3 kinds of bonding. Ionic, which is a metal to mono, covalent, non-metal to non-metal, metallic, metal to metal. There's some numbers here. I'm going to talk about that in a subsequent podcast.
Yep.
Covalents are the weird ones. They're like uber complex. They either have polar molecules or non-polar, or they have network solids. And then we've got something called hydrogen bonds and dipole forces. We're going to kind of put some meat on these things as we go farther. Okay. All right, so those are intermolecular forces. Now let me kind of get this all figured out. Intermolecular force is an attraction that exists between molecules. And so here I have a molecule. This is a water molecule, let's say, because it's got that bent shape.
Okay, that's Oregon State.
There you go.
And that one there's UCLA, and they're playing each other in basketball.
Right. And so there's a dashed line, and it's very important to understand. When I talk about an intermolecular force, it's kind of a bond, but it's really not as strong as a bond, so we don't use the word bond. The word bond indicates a lot of strength.
Right.
And a force is not very strong.
No.
So
it's an attraction.
It's an attraction. So it is a bond, but it is a very weak type of a bonding.
Yeah.
So we don't call it a bond, we call it a force. There turns out there are 3 kinds of intermolecular forces. All right. Now, let's just kind of illustrate so you make sure. An intramolecular, remember that's when I played
intramural within the same school.
That's the covalent bond.
Right, because it's
and
within the same
covalent bond
molecule.
is really, 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 really strong.
Yeah.
It's the strongest bond that there is. That is the covalent, intra. But when we talk about intermolecular, that is the bond between. This is very weak compared to this. Strong and
Sams.
weak. There you
Mr.
go.
Burke.
Yeah, right. All right, a bunch of definitions. The 3 kinds of forces. In fact, one even has the word bond because it's the strongest of the 3. I want you to copy these down, push pause, and then I'll talk about it. Okay. So the first force is called the dipole force. The force exists between positive and negative ends of polar molecules. I'll illustrate that in a minute. Hydrogen bonds, a form of dipole attraction. So it's similar to a dipole attraction is dipole force, in which a hydrogen atom is bonded to a strongly electronegative, oh, there's that word, atom of another electron-rich atom. And then the last one is the London force. This is where you have basically non-polar molecules attracted to each other, and we call that an instantaneous dipole. All right, a lot of words there, and we'll illustrate each of these one at a time. So let's talk about the dipole force. It is between 2 polar molecules.
So if it's a nonpolar molecule, no dipole.
No.
It has to be polar.
It has to be polar.
To have a dipole.
And basically what happens, if you have 2 polar molecules, you'll have one end that has a negative charge and another end that has a positive charge. That's the definition of polarity. They're like
positive,
little
negative.
Magnets, right?
Yeah.
And basically the little magnets come opposite each other. And again, it's that whole concept that positive things are attracted to negative things. Again, this is the dipole force, or the dipole-dipole force, sometimes it's called, and opposites attract. So it's opposites attracting. That's how the dipole force works.
Okay.
The second one is a little similar, but it gets confusing. It's called the hydrogen bonding.
Right.
It is basically a strong type of dipole force.
So it is a dipole. It's just especially strong dipole.
And it is always between hydrogen, since it's called the hydrogen bond, and either fluorine, oxygen, or nitrogen.
Phone.
You might think of E.T. You guys remember the movie E.T.?
They probably don't.
Well,
this came out when I was 3, Mr.
Okay,
Bergman.
I was in high school, so I think, or college, or whatever it was. E.T.
Not due for a remake on that one. I would
Yeah, they
imagine.
probably ought to. Yeah, but anyway, E.T. when he got into the classic, he said E.T. phone home.
Yes.
Well, if we misspell phone,
F-O-N.
F-O-N, phone home.
Ah.
And you see, these are the 3 most electronegative atoms that exist. F, O, and N. F, if you recall from previous podcasts, is about 4.0, and he's 3.6 or 5 or something
3.0, actually.
He's 3.0, and
Yep.
O is
Somewhere in the
3.5
middle.
or something like
Yeah.
that. These are the most electronegative atoms connected to the smallest atom, hydrogen, that bonds. Helium is smaller, I guess, but it doesn't bond.
Okay.
So these are the most electronegative atoms. And it works like a dipole-dipole, but it's just stronger. And it's about 5 times stronger as a rule.
All right, we're here at the World War II Memorial, and we don't have any amazing chemistry concepts, but we do have some amazing water, so we wanted to take this opportunity to talk about water. Water is polar, and the fact that it's polar makes it have a ridiculously high boiling point, much higher than it actually should, but and not only is it polar, but it has hydrogen bonds, which are very, very strong intermolecular forces, gives it a very high boiling point.
Nice.
Okay. Now, the London force, sometimes called the London dispersion force, go right here, which we abbreviate LDF, is between 2 nonpolar molecules.
Okay, so if you have 2 nonpolar molecules, it's an LDF.
That's correct.
The end.
That's right.
Okay, that's
What
easy.
causes that, though? It's caused by momentary dipoles. Momentary dipoles.
Yeah.
All right, here's an example.
Please explain.
Classic example is oxygen. Oxygen this is oxygen, O2. You know, if I draw the Lewis structure, one thing when you're doing these, folks, you have to draw Lewis structures.
Yeah, when you're determining
again.
Yeah, if you're determining what kind of force it is, you have to always draw the Lewis structure first.
Determine its polarity.
Determine its polarity.
By its shape and its bond electronegativity deal.
And then you can determine what type of intermolecular forces you're dealing with.
That is correct.
Had to make sure I got the right tra.
Yeah.
Okay.
So here's my oxygen molecule with a bunch of electrons. But one thing we've learned about electrons from forever ago now is that electrons are not static. They move, so to speak. They move around. So if they're like this, that's true. But what happens if this electron, for just a moment, moved over here, and he's no longer here?
Then
this electron right here moved over here for just a moment.
Well, then if the electron moves, it carries its negativeness with it.
That's correct.
And it moves the area of more or less negativeness with it.
So it would make this side of this atom, or this molecule, negative over here.
Right, because it moved
and this
to the right.
side-ish positive.
Right.
Well, if the same thing happened on this side, and it was positive, and this side was negative,
Hey, opposites attract.
Opposites attract, and you get a
Well,
very, very weak...
You're kind of attracting a positive to a positive there,
Oh,
Mr.
yeah,
Bergman.
I did it wrong. So, it would be attracted to here.
There you go.
And they would flip, actually. That's called a London dispersion force. Now, you probably know this, but oxygen is not a solid at room temperature.
It's a gas.
It's a gas. We're breathing it in right now. So therefore, they're really not attracted at all. But if you cool it down enough, this force is what causes the O2 to connect to the O2.
Liquid oxygen. Cool stuff.
Very cool stuff. Here's actually the picture that I meant to draw, and basically positives with negatives. You may want to print this out if it just shows you just the momentary movement. I moved this electron here, and I moved this electron here, and that's how I did it. I forgot.
All right.
Now, there is sort of another interesting thing. Now, when we think of nonpolar things, we think of things that have very, very low melting points because they have very, very weak bonds. But some things actually have very high melting points, and that's because instead of being one London dispersion force, there are many. So here I have...
It's like the fuel that you put in your car. It's a nonpolar compound, or many nonpolar compounds, but it's still liquid.
Yeah, so one thing that goes into gasoline is hexane. There's a small amount of hexane in gasoline, I think it is at least, right?
I know there's toluene. I don't know.
Oh, well, but anyways, you could burn hexane.
Well, we'll
I promise
pretend.
you. And I know it's a liquid. This substance is a liquid at room temperature because I've
We have
played
some in
around
the
with it.
stockroom.
So,
I
but
think.
why does it stick together? Well, it turns out these are all nonpolar, So you'd say it's a London dispersion force, but if you have lots of atoms, there's lots of electrons. So you can have lots of London dispersion forces, and if you take them and you add them together, they can add up to a relatively strong force.
I feel an analogy coming on.
Yes, I have an analogy. Have you ever played with thread? Like thread, like that when you're sewing.
Yes.
It's very easy to break. You
Right.
could snap it. But what if I took, say, 100 pieces of thread and intertwined them together?
Into a larger string or rope.
A rope.
Stronger.
And much stronger. You
Right.
see, individually they're weak, but together they can be strong. So there's even nonpolar things that are solids because they're just bigger
Right,
molecules.
like iodine crystals, iodine
Yeah,
crystals.
lots of examples
Yeah.
of these, like wax from a candle.
Oh, yeah.
That's nonpolar, and
Yeah.
that's, it can be melted relatively easy, but it is a solid.
Yeah.
Okay, so here's something we should say, just a summary of that. The larger the nonpolar molecule, the
Higher.
higher the boiling point. And why is that?
More electrons equal stronger bonds.
More electrons equals more
More LDFs.
LDFs.
Yeah, it's a better way of putting it.
Yeah. Okay, now one more thing that we want to cover is the network solids. Now, in a network solids, this is a substance that does not have intermolecular forces,
Right.
none of them. It's all covalent bonds, 100% covalent bonds.
Okay.
And these only happen with compounds of carbon and silicon.
Now we need to be careful. It's not any compound with carbon in it. It's a
Yes.
compound of pure carbon.
Carbon
Only.
only. And with silicon, it's actually usually
Silicon
silicon
and some
and
stuff. Oxygen
usually oxygen.
Not
I
always.
think
Yeah, you can do it with other stuff too.
not many though.
Not many. But carbon, it has to be carbon only. It's not like carbon and hydrogen, because that's definitely not.
Yeah,
never
we'll show you
solid.
some examples of that.
Yeah.
In fact, we'll hear some examples.
So-
This is a diamond.
Okay.
A diamond is made up of all carbon, carbon to carbon to carbon. It's in a tetrahedral
Yeah,
arrangement.
that
This
looks
is a
like
piece of
graphite.
graphite. Graphite is carbon to carbon to carbon in a slightly different arrangement. I'll show you that in a minute. And this is a crystal of quartz. And that's silicon and oxygen. I forget the exact formula. SiO3, I think, isn't it?
Two. Sure.
Okay, graphite. This is graphite, and you
All
can
right.
kind of see this is the bonds, and actually there are London forces. This is kind of a complex one, but it is
Yeah.
these are the hardest substances known to man. These network solids, and you can kind of see this is the structure of graphite.
Yep. And those sheets of graphite that you can see, the layers, they kind of slippery. They slide on top of each other. That's why
Because
graphite
of
is
the
slippery.
London forces, but
Right.
between the sheets, they're very,
Right.
very, very
Those.
strong.
Yep. Between each molecule.
Okay, now diamonds are pretty cool.
Yeah.
I think we should. There's a,
Oh yeah, I think this moves if we click on
yeah,
the
let
link.
me click on the link here. So here is the crystal right here
Yeah,
of
it's a
diamond. They're
tetrahedral
all
arrangement.
tetrahedral. Remember that bent or the 109-degree angle, and they go on and on and on and on. And so that's what the diamonds look like. Okay.
All right.
Now we had a visit a while back, Mr. Sams, to the Smithsonian Institution, and we got to see certainly the most famous diamond in the world.
Yeah.
And I think we should take a slight tour there.
Well, let's do it.
Okay.
All right, what you just saw there is the Hope Diamond. It's a classic example of a covalent network solid. All the carbon atoms are arranged in a tetrahedral shape, which makes it one of the hardest substances in the world. The hardest substance, actually, in the world.
That's very cool. I mean, the coolest diamond in the whole world.
Big.
And it's really, really big, and that's just really cool. Okay, quartz. This is quartz, and we can kind of see his structure. And I think, Mr. Sams, I think you're right. It's SiO2, and that's quartz crystals. And I think the red is the oxygen, and the gray is the silicon, if I'm not
Yep.
mistaken.
Looks about right.
And actually, while we were at the Smithsonian, we also saw a huge piece of
Quartz.
And so
Let's
I think we should visit the
take a look.
Smithsonian for just a minute again.
Another example of a network solid is quartz. And this piece of quartz is absolutely gargantuan here at the Smithsonian. It was found in Nambia, Africa. So this is silicon dioxide, SiO2. Huge piece, isn't it?
Again, that was really, really cool.
Big.
Big. All right.
There's a lot of quartz around here too.
Yeah. There's quartz.
Yeah, big chunks of it kind of within the granite.
Yeah.
If you go ever,
Those quartz mines.
Local people, if you ever hike up on Wallow Canyon, there's a little outcropping you can climb down to.
Yeah.
Yeah, it's pretty cool.
Hey, and lastly, let's just kind of summarize this as it all goes together. So we've got bonding, and you always have to, first of all, just determine what type of a compound, metal to metal, non-metal to non-metal, metal to non-metal.
Right.
And then when it's covalent, you got some more work to do.
Yep.
You then got to draw its Lewis structure. So after this, you got to draw the Lewis structure. Once you do that, well, actually, unless it's just carbon and the silicon, you can just jump over here to network solids. But if you draw the Lewis structure, you've got to determine if it's nonpolar. If it's nonpolar, then it's a London force. If it's a polar, then it's a hydrogen bond or a dipole force, and you have to determine by this the ET phone home method.
Right. If it's a phone home molecule, then it's a hydrogen bond. If it's not, it's a dipole.
Yeah. Okay. So that's how we do this, and we got one more podcast.
And
on
we'll do
this
some
topic.
practice with that.
And we'll do some practice with this table. Okay.
Bye.